Find the Fourier transform of this two-sided decaying exponential. Let's solve this problem step by step together. The Fourier transform of any continuous time signal is defined as the integral from -infinity to infinity of that signal times e to the negative j omega t dt, where omega is the angular frequency. In this case, our signal is e to the negative a absolute value of t, which is defined differently on both sides of the origin. On the positive time axis, this is e to the negative at, the decaying exponential, but on the negative time axis, this becomes e to the positive at, the growing exponential. So, we're going to have to split the integral into two pieces. And then, using laws of indices, we can simplify the integrands into a single exponential function in each case. We have e to the power of at minus j omega t for the first integral, and the second one is the same thing, but with a negative sign in front of the a. And now we'll factor out a t in each case. So, the Fourier transform of x of t, which we can denote using this fancy f operator, or by capital X of j omega. And this capital notation is not unique to the Fourier transform. We use it in the Laplace transform, the phasor transform, any frequency domain representation. Now we'll integrate both exponentials by maintaining the exponential parts, but dividing by the coefficients, and then we'll plug in the bounds. Here it's implied that we're taking the limit as t approaches infinity or negative infinity. It's an engineering course, so formality is not of the essence. We get 1 over a minus j omega in the first case, and the second piece becomes, well, let's take the negative outside, like this. And now, at infinity it's 0, at 0 it's 1, so we have 0 minus 1, and the negative sign gets cancelled out. Okay, so this is our capital X of j omega, but there's actually room for simplification. The denominators are complex conjugates, so if we give the fractions a common denominator, j omega cancels out, and we end up with 2a over a squared plus omega squared, a purely real function of omega. And so, a single pair of axes are enough to draw the frequency spectrum of this signal, when usually you would need to draw the magnitude spectrum and phase spectrum separately.